now we continue. So there are a few things that I still need to cover in order to us to complete the first part. These remaining materials are not quite related to the main storyline, so it's a kind of information that we don't need to know in details about the physics behind that, but it's better just we have that in mind. I think pulse echo tick that already. Yes. Okay, let's see. Now the first one is the yeah. So today we'll talk about the wave speed. On a transverse wave, not on a transverse wave. Wave speed of a transverse wave on a string. Okay. So where the idea will be, we have learned that the wave speed of a wave depends on the medium. We emphasize this frequently. In particular, if you talk about the sound, the wave speed is 340 meter per second in air, is equals to 1500 meter per second in liquid, or is 3400 no 3000 meter per second in solid. And for example, this is an example for sound, and this also similarly for example of the speed of light in different media, but we'll talk about it in the next chapter. But we in the school we can easily demonstrate a wave using a string by vibrating that string up and down. Then we produce a transverse wave. So we are also interested to know how would that speed of transverse wave depends on the medium. So after all, it's just a string. So what kind of thing we can do to change a string as a medium? So it turns out that the equation, we don't have any explanation for it. This is just an empirical formula what we obtain from experiments, and then this is V equals to square root T over mu. So V is the speed of light, the speed of transverse wave on a string. It is measured in meter per second. Well, T is the tension in the string. Will be in Newton, and then mu will be something new. It is called the per mass per unit length. Of the string. So this unit is mass per unit length, so it's kg per meter. Well, let's stick to DSE notation, meter per second. This. So essentially, the tension is the force you exerted on the string. It means that how large the force you exert on it, while on the other hand, mu will be how we talk about like how heavy the string is. Okay, so maybe I take an example because this has never been tested quantitatively in the examination. All you need to know is just qualitative understanding. But instead of just telling you qualitative features, then I think why not just give you the equation to refer to. So let's take a example. Anyway, so let's say we are given a string. This is string, and this string, it turns out that it has a mass of I don't know, maybe mass of, let's say, 400 gram, and then it is of, let's say, 2 meter long. And what you do is that you put this string on a pulley. Such that now you exert a known tension by exerting a mass on it. And then here, the mass you attached to it is, let's say, 3 kg. Then what you do is that you just want to produce a wave here, and then let the wave to travel. And then the travel is traveling at a speed of v. Okay. So I intentionally include this kind of setup because I want to demonstrate to you that how we usually find out the tension in the string. Because in the classroom demonstration, what we usually do is just we ask two classmates to hold a string at its two ends, and then that gives us a tension to the string, but it is hard to measure the tension on the string in this case. So in a laboratory, what we usually do to ensure that we have a precise information about the tension on a string, we will set up a pulley like this, such that you can ask the mass to exert the tension on a string. While mass is easy to measure accurately, so therefore this is a good way. So let's do the calculation then. So to find a V, first of all, we notice that we're using V equals to T over mu. Well, T will be just the mass, the tension exerted on the string. So in this case, it comes from the mass attached. So you just use mg. So I use 9.81. So this will be the tension. Well, on the other hand, the mu will be equals to, but denote this as this. This is less d to m, this is big M, and this is the length, like this. So the tension here, we use the capital M. While for the mu, then we use the lowercase m divided by the length. So it's 0.4 divided by 2 kg per meter. Then we substitute all this into V. Then we can get the answer. Then this will be 12.1 meter per second. So therefore, when you send a pulse on this string, then its speed will be 12 meter per second. Okay, now this is how we find out the wave speed on a on a string. Well, so these actually can also lead to a detailed experimental investigation. But however, we usually will not do this experiment because this wave speed, in order for us to measure this wave speed, you will need to prepare a very long string, because you see, with this kind of reasonable estimation, the wave speed is actually very fast. So that means this pulse, whatever you send to it, it will have a very high speed. So therefore, within 1 second, the pulse will travel 12 meters already. So there is another way we can measure the wave speed on such a system without really allowing the wave to travel along the string. That is using the technique of stationary wave. But we will not talk about it now. At this moment, I just want to get your attention to the fact that we have one equation to be used for transverse wave on a string. Okay, now another kind of question is we want to address here is about the measurement of speed of sound. In particular, we're only doing the one in air. So we know that, or we are given in most questions that the speed of sound in air is 340 meters per second. But the question is, well, how do we know? Because after all, although it is just a speed, you may say to find speed, we can do it by having distance over time. This is you can take as an average speed. We can use the average speed to do that because we know that the speed does not change with the medium. So we just use the distance travel over time taken for us to measure the speed. Well, however, this speed is not small or low at all as compared to the speed we study in the mechanics. Well, it travels 340 meters per second. So that means in just around 3 seconds, that speed of sound can already travel over 1 kilometer in 3 seconds. So therefore, if I really travel so fast, it means that usually if we just have a tabletop experiment that you let the sound to travel for, let's say, at most 3 meters, let's say, then the time taken will be very short. You can do a rough estimation. If you do that just at a tabletop experiment, that let's say you allow the sound to travel for 3 meters, then the corresponding time that it takes will be less than 0.01 second. So this value is so small. So there is no way for you to really to find it out. So therefore, what we usually do instead is that we need to have some electronic devices to help us. So small for human measurement. So therefore what we do is that we need to have something called the oscilloscope to help us to take the readings. So this is the idea. So the experimental setup will be the following. Well, what you do is that first of all you let a path for the sound to travel. This one will be just a ruler. And then on this ruler, you put two microphones at two different locations. These two microphones is connected to a so-called oscilloscope. That it can detect the signal received from the microphone. This microphone 1, microphone 2. And then this will be connected here, and this will be connected here. Then on the screen, then you will receive the signal. Then the screen will project the signal where you receive any signal from microphone 1 and microphone 2. So, and then what you do is that you have to have a source. For example, you make some noise on some place here, on a certain position, let's say. So you put a source. It can be just a speaker producing a beat or a pulse. Or just a pulse source. Then, when it really produces a pulse, then this will travel and then hit the microphone 2, generating a signal, and then at later time it hit the microphone 1 and generate another signal. So this will basically be the pulse that should travel along. Then on the oscilloscope, what you will find on the screen will be a grid. Let me something. Okay. Maybe we find something like this. So on the screen, you will find a grid like this. Each box here is called a square, or we call it a division. Division. And then for each division is actually refer to a certain time scales. Well, what is this? This is essentially just a displacement time graph. Now, as it receives a signal, let's say you produce a pulse like this, and then later on the screen you produce another pulse, let's say located here, like this. So this pulse refers to the signal received by the microphone 2 when it detects the pulse. While this red pulse refers to the signal produced by the microphone 1 when it detects the pulse. And then we can just go ahead to measure the corresponding time delay. Let's see, there's so many things here. So on the screen we look something like this, and then we see these two pulses. Then what we do is that we need to read on the screen to count what is the corresponding time delay. Well, for example, here you see the time delay is about like 0.5 division, 1.5 division, 2.5 division, 3 divisions. So here you notice on the screen that the time delay is 3 divisions. Then 3 division refer to a certain amount of time. Then that goes back to the oscilloscope setting. So there is a setting so-called a time base on the oscilloscope. It tells you certain amount of second. For example, it tells you in this case I have 10 milliseconds per division. This all goes back to the setting of the oscilloscope. So this one is with time-based setting. On the screen or on there's many buttons on the oscilloscope. Then on one button it will show you the time base you're using. Then therefore from this we can calculate the corresponding time delay. The time delay will be equals to 30 milliseconds. So from that, let me do some math first. Maybe I take another one here. Let's take this like this. So it's 3 milliseconds. So therefore, it means that the time taken for the pulse to travel from the second microphone to the first microphone is 3 microseconds. Microsecond? No, 3 milliseconds. And then after that, then I get the time. Then I can just also measure using the ruler the separation between the two microphones. Hence, we can get the distance. So I measure distance traveled, and let's say I rate it to be 1.2 meter. Just a rate on the meter rule. Then this is like 1.02 meter. And then I can calculate the speed of sound. This equals to 1.02 divided by 3 times 10 to the power minus 3 microsecond. This is 10 to the power minus 3. Then we get to 340. This is so accurate. This. So essentially the whole spirit here is that we use the oscilloscope to help us to measure the time instead of using a timer, handheld timer operated by a human, because the speed of sound is really too fast that you can't just use the timer to really track its motion. Well, you may ask, and then how about can I use this method to find out the speed of light? Well, it turns out that it cannot, because somehow the speed of light is really too high that even for these kind of apparatus you can't really measure the time delay. For the speed of sound, we can still use this apparatus so that we can see the time delay on the screen. The two pulses are separated away from each other far enough, but for light, the time delay is so small that these two pulses almost superpose with each other. Then in that case, you cannot do anything. We need to use some other method to find out the speed of light. Okay, next one that I want to talk about will be the reflection. So technically you should have learned reflection in junior science. Here is just a recap. So we have something called the law of reflection. Where you have a reflecting surface. For example, a mirror. And then we need to incorporate a normal there. And then by observations, we found out that the ray coming in will be reflected in this sense, such that the angle of incident, theta I, is equals to the angle of reflection. And this is the so-called law of reflection. So it's called angle of incident is equals to the angle of reflection. So it's theta I and theta R. Now for most of the time, we just need this kind of diagram because we are working on a paper and the paper is just 2D. But there is also a little bit on the remark that when we are really talking about reflection, well, in real life it will be 3D. So therefore, we have to make sure that everyone are on the same page. Now we have the normal here. And then right now, the reflecting surface will be the one underneath. This will be the reflecting surface. And then when you have really a light ray coming in, I denote this yellow plane as the plane enclosing the normal, the dotted line, and the ray. Now, then the law of reflection, the complete version of law of reflection should talk about that this reflected ray is on the same plane. So not something like this. Because now it is like 3D now. So therefore this 3D version will at least make sure that we are not having some misconception. Or when the question suddenly talk about, oh, I'm talking about the plane and then, well, but another reflection, I never heard about the plane, or, well, actually it is in the statement. But just like 95% of the time, we never talk about it because we always just stick with 2D. Okay, so now as a law, we don't have any explanation like Newton's law. It's just a law means it's a summary of the observation we make in daily life. We saw this happen so frequently, and therefore we summarize what you observed and then make it as a pattern, make it as a law. There is no clear, does not aims to explain anything. Now, so then what can we learn about, what can we do about with it? It seems really easy. Well, first of all, let's see some little bit non-trivial example first. Well, first of all, if the surface is tilted, then the corresponding normal will also be tilted. First of all, needs to make sure that no one will make this mistake anymore. Some students, they will always think that the normal is always vertical. That's not true. The requirements to call this dotted line as a normal is that this dotted line is perpendicular to the surface. So when the surface is tilted, the normal will also be tilted. And then in this case, then I will have the ray coming in. I will have the ray What's that? So I will have the ray to comes in, and then it get reflected like this. So this is these two angles. This is theta I, this is theta R, and they're equal. Okay, so even it's tilted, it still work. And that is a special case that of a special interest, which is a so-called what's this called? Yeah, the mirror corner. So it will have 90 degree like here. What we do is that when you have really a light ray coming in, let's say going in random direction like this, then it will reflect it to here. And then it turns out that yes, as long as this is like a mirror corner, then you have this to be 90 degree. Then the light ray will be reflected such that these two are parallel. This one can actually be explained by many geometry. Now my drawing is really definitely not good here. How do I don't have protractor on the screen. But never mind. No, I think you just make it more difficult. Let me do it well. So at least I'm not talking like this. Not like this, okay? So that this angle equals to this angle. And let me make a number. Let's say I call it like 15 degree here. Then this is 15 degree. Then this will be 90 minus 15. So this will be 75. Then this will be 15 because you have a triangle here. And therefore, when this happen again, the angle of incidence here will be 75. Well, by the law, this will be like this, and this will be 75. Well, then that means this is 15. So what you find out is that we rely on what you learn from trigonometry. This angle plus this angle will be 180 degree. Well, therefore it means that these two are parallel. So this one has a application. For example, what application? Because it means that when you use this kind of device, you can just reflect the light ray. It doesn't matter which direction does it come from. It can come from here. It may come from here. It may come from here. In whatever direction you send the light ray to it, it will be able to reflect it back along the same path. So therefore, this can be used in many ways. For example, we use it on a bicycle. Let's say we draw a bicycle. It's a bicycle. Okay, someone on the bicycle. Like this. And then, well, it's very dangerous to drive a bicycle at night. So what they do is that you put a mirror corner at the back, 90 degree. So therefore, when we have a car comes by, well, the car must open its front light. Then any light comes by, shining to it, it will get reflected. And then hopefully, then the person will be able to see, or the driver able to see. So therefore, you don't need to have really a light source installed on the bike, but you can still as if it is have a light source already. But that light source is actually coming from the reflection of the front light, the headlight of the car. And another useful thing is the Earth Moon observation. The moon very far away, and okay, just not to scale. This is the Earth. Well, all we do is that we put a mirror reflector there. Then when you're on Earth, you send any signal to the moon, they will get reflected on Earth. Then in this case, people can use this information to, for example, look at the time delay, and then can find out the distance between the moon and the Earth. And it turns out that what we find out is the Earth is moving away from us. For students who are interested in this, you can go to find out, understand why. And it is about at the rate of a few centimeter or millimeter, I forgot, for every year. I think it's like 0.01 centimeter, I forgot, but this is there, the data for that. Okay, so this will be the reflection that I want to talk about. There's some question about the pulse echo technique. I talked about it already last time, but this is just a reminder that you need to take care of the factor of 1/2 when you do the calculation. And other part is our electromagnetic spectrum and the applications. Well, that one I just mostly just facts. Let me see. In the past, I just asked them to self-study it, but I have the PowerPoint. I got some headaches. Okay, I think anyway, for the electromagnetic spectrums, I just let you to study yourself. Electromagnetic spectrums. So you need to self-study it. Well, in particular, please pay attention to the wavelength and frequency of each types of electromagnetic waves, and then also pay attention to the applications. For example, what do we use for let's say microwave, radio wave, things like that. There are some numbers that I definitely need to recall. For example, for visible light, you need to know the wavelength is 400 nanometer to 700 nanometer for visible light. Well, for application, there are many. At least for each, tell me one. Radio wave, it will be used for broadcasting. And then infrared, no. Microwave can be used for cooking or satellite communication. These two usually don't want to talk about each other and say, because on the Earth we have the atmosphere, or actually we should talk about as an upper atmosphere where there is some ions there, and the satellite is outside. So for radio wave, it turns out that you cannot have radio wave to penetrate this atmosphere. It will just reflect by the atmosphere. That is also the reason why radio wave can go very, very far away, and the soldiers use, the militaries use this for the in the World War I and World War II. While for the microwave, they can penetrate through the atmosphere, so they can use the microwave to communicate with the satellite. And the infrared is for cooking or thermal camera. Visible light can be used for, what's it called, fiber, optical fiber, or forming images that you take photo. And you have UV light will be sterilizing or seeing internal structure. And the X-ray also see internal structure. Gamma ray will kill bacteria, sterilizing. X-ray also, internal structure can be X-ray, sorry. UV is not internal. UV usually is for, this is called fluorescent light. Fluorescent light. Like this. There's still many more. The textbook gives you many examples, but I think as a student, well, when you need to do examination and memorize all of them. But no need to be in details. Just something you heard of it that will be good. So for this part, please make good use of your textbook. Your textbook is very nice in the sense that it gives you many examples. For most of the time, those examples are not really necessary, but for applications, those examples will be very useful. Please go through there to take a look. Well, and then I take a break first, and then afterwards I come back, I will talk about refraction.